Thanks, Jacob, for the invitation, and thanks everyone for being here. It is a pleasure. And so today I'm going to be talking about how we can come up with an equation function for a very broad class of experimental design tasks. So hopefully there's something interesting for people doing, kind of like more sophisticated Bayesian optimization loops. So naturally, I'm going to be talking about AI-assisted experimentation. I'm pretty sure most people here are pretty familiar, but let me do this very quickly. So there are two components. On the top panel, there is the AI experiment designer, and this algorithm is going to be selecting the experiments that are going to be performed. We're going to denote the experiments as X. This is going to be an input to an experiment platform. You can think of this as an expensive simulator or a wet lab. And then from the experiment platform, we're going to get some output, f of x, and this data is going to be used by the AI experiment designer to select new experiments in an iterative loop. So in most applications that we care about, these experiments are expensive. So that means that the AI experiment designer has to be really efficient selecting these experiments. So in order to support this efficiency, there are two important aspects in algorithm design. So the first one is that the AI experiment designer has to be aware of the design goal, right? So it needs to know why we're collecting this data. And one classical example is optimization. So maybe we want to find the X with the largest possible value of f of x. And then the second aspect that I'm not going to be talking about in this talk is the prior knowledge. So the information that we have before we run any experiments. So at the heart of computing efficient experiments, there is this concept called the value of information. And I'm not going to give a formal definition. Actually, there's not like a single definition. So this depends on the context and kind of also the community that is talking about this. But the idea is that the value of information quantifies how much information we could get from running a specific experiment X in support of our design goal, given the information that we have so far. So at each iteration, we want to select the point with the highest value of information. And in this traditional setting, let's say where the design goal is something relatively simple, such as finding the X with the largest possible f of x. Things are well understood from prior work. But as soon as we move away from this design goal and we start looking at more complicated goals, then computing the value of information actually becomes really hard. And that's the focus of the talk. So how can we quantify and efficiently compute the value of information under complex design goals? And this is based on a paper that appeared at NeurIPS last year and also some ongoing work. So let's see how traditional Bayesian optimization fits into this picture. So essentially what happens here is that most BI algorithms have these two components. One is the probabilistic surrogate model of the objective function, and then this is used to build an acquisition function. I don't want to spend too much time talking about these two components. In particular, I'm not going to be saying a lot about the probabilistic surrogate model, and I'm going to focus on the acquisition function. So to motivate why the acquisition function is important, let me conduct a very quick thought experiment. So suppose that we're trying to find the maximizer of this function, shown as this dashed gray line. That's the underlying function. And we have collected some data. So we have evaluated this function at a few points. Then we build a probabilistic surrogate model. Here I'm showing a GP. Then the question that I'm going to pose is, what point should we choose next? And I don't think there is an obvious answer. I guess for most people, unless you're a BO algorithm, you probably don't know exactly what to do. But there are two intuitive answers, which is selecting the point with the highest mean, right? So this is the point that my model is saying has the largest value in expectation. And the other option is selecting the point with highest uncertainty, right? So the point where my model is most uncertain about. There's the theory, right, that says that actually neither of these two choices is optimal, and what we want to do is to strike a balance between exploration and exploitation. That's what the acquisition function is trying to do. And there's not a single choice. There are actually multiple options for acquisition functions. Here I'm showing a list of the most popular equation functions, and I'm going to go back to this list later on my talk. So in the literature, many people have talked about equation functions for specific design goals. Global optimization, which is described by Bayesian optimization, is what most people have focused on, and there are all these equation functions for this task. There are also other tasks that are also popular, and you can find some work on things like level set estimation, on something like diverse.k optimization. However, in practice, design goals can be really complex. So just to give you a very quick example, suppose that we want to design a portfolio of antibodies, so not a single antibody, actually multiple, that are, so that this portfolio is effective against potential antigens mutations. So essentially what we're trying to do, suppose these are all possible antigen mutations, and we want to develop a portfolio of size 3, a portfolio of antibodies of size 3. Then essentially we want to build this portfolio so that we can cover the different mutations, right? So we want this antibody to be effective against these two antigens, this antibody is effective against this antigen, and this other antibody is effective against these two antigens. So how do we actually formulate this? Again, might not be clear, but some collaborators actually suggested that this could be a suitable formulation. So just to, let me quickly introduce some notation. So let's denote the antibody as W, the antigen as C, and then suppose that we can compute the performance via simulation, or an approximation of the performance via expensive simulation, and I'm going to call this S of W and C. And we also have access to a distribution over potential mutations, which can be estimated from some prior data. Then we can formulate this as this complicated combinatorial and stochastic optimization problem, right? And this sort of capturing the intuition that this portfolio of antibodies is going to be good in expectation when we get a random antigen and we select the best antibody in our portfolio. This sort of captures what I was describing before. So even for this task that still can be formulated as an optimization problem, it's not clear how one can adapt one of the equation functions that I mentioned before to solve this problem. So let's go back to this figure very quickly. So again, we're asking this question. So given that I want to solve this more complex design goal, then how do we quantify the value of information, and more generally, what does it mean to balance exploration and exploitation in this setting? And I think it becomes much more challenging. So let me formalize the problem setup, and then I'll tell you what the strategy is. So here, instead of supposing that the goal is to find the maximizer of the function, the goal is to find what I'm going to call a target set. I'm going to use this notation to denote this target set. This target set is going to be computed via some efficient algorithm. So this algorithm is, we assume we have already access to the algorithm, and it's something that we could apply to find this target set for cases where the function is not expensive, right? And you can think of this as perhaps a cheap optimization algorithm, or something else if the goal is not optimization, that you could use on a cheap function, but it becomes infeasible when this function f is expensive to Adobe. So that's the problem setup, and actually it is something that was proposed by Ines Wanger and collaborators in 2021, and this is the original reference in case you're interested. Okay, so let's go back again to these different equation functions. Which of these equation functions can actually be generalized to handle this new, more general problem setting? And I'm going to show you that posterior sampling, also known as Thompson sampling, can actually be generalized to this more general problem. So before I describe the algorithm for the general problem formulation, let me actually describe what posterior sampling looks like for regular Bayesian optimization. So again, this is an objective function, and we're trying to find the maximizer of the objective function, so this point around here. The first step is to build the surrogate model. And then what posterior sampling does is it draws a sample from the posterior distribution. So it's this purple line shown here, and then it simply selects the point that maximizes these samples. So that's posterior sampling for Bayesian optimization. So in pseudocode, this is what it looks like. So we have our initial data set and our prior. Then at every iteration, we're going to sample from this posterior, and then we're going to select the point that maximizes this posterior. Right? Then we observe and update our data set. Then one sort of naive idea is to simply replace this argmax by the target set that we're trying to estimate. And in principle, that's a valid algorithm for this Bayesian algorithm execution problem. Turns out it is a good idea. And here in this step, let me just emphasize that in principle, there are multiple ways in which this point could be selected. So we have this set, and I'm not telling you how to select it, but one way in which we explore in our work is selecting the point with highest entropy, so the point with highest uncertainty. So now let's see what this algorithm looks like for a level set estimation problem. So again, now we have this function and the same data, but this time the goal is to find the level set. So all the points so that the objective value is above this threshold. So what this algorithm that I just described is going to do is going to, again, draw this sample from the posterior distribution. This is going to imply some level set associated with this sample, and then we're simply going to select among the points in this level set the point with highest uncertainty. So this point around here. So that's the algorithm. So like I was saying, turns out this algorithm is pretty good empirically. So here I'm showing the results for this antibody portfolio problem that I described before. I don't have a lot of time to go into the details, but this is using pre-collected real-world data. And we see that this algorithm achieves much better performance. So here, lower is better than an information theoretic algorithm that was proposed in this original paper by Niswanger and also by Random Bayesian. And we have results for different tasks, so not only this portfolio problem. And in general, we see that this algorithm is pretty robust. So it achieves results that are at least comparable with baselines. But this algorithm is much faster because it avoids some complicated information theoretic computations that I'm not describing here. And then, so I'm kind of running out of time, but I just want to say something about the theoretical insights. One natural question is in which cases or what makes this algorithm suitable for estimating these target sets? And it turns out that in principle, it's not an algorithm that you can apply all the time. But there is some notion that we introduced in the paper called complement independence, that if this notion is satisfied, and the intuition is that if somehow you are told that one point is not in the target set, then the algorithm doesn't need to evaluate the function at this point to find the target set. That's sort of like the intuition, but there is a formal definition. So what we show is that if this condition holds, then this algorithm that I described actually finds the target set. Okay, so let me recap very quickly. So the benefits of this algorithm, it is computationally efficient, so much faster than existing baselines. It delivers a very strong performance. It is straightforward to implement, so if you have access to this algorithm A, then you just need to apply it on posterior samples, and there is some theory guaranteeing that it is convergent in a very broad set of cases. As future directions, I think Bayesian optimization has been really powerful, and there are some extensions such as Bayesian algorithm execution, and then the natural question is what framework is going to arise in the future to address the complexities of real-world problems. I think there are many interesting opportunities in this area. And some super quick advertising. I recently joined MBZ-UI as an assistant professor, and I'm hiring PhD students for the next fall. So if you're interested in Bayesian optimization, generative models, and similar problems, feel free to reach out, and the application deadline is December 15. Pretty close, but if you're already planning to apply into other universities, and this should be pretty feasible. So with that, I'm going to stop. Thank you so much.